All right, welcome to This Explainer. Today, we are unpacking a seriously fascinating architectural shift happening right now in AI. We're talking about the evolution from simple, isolated AI agents all the way up to massively collaborative, graph-grounded swarms. So if you're out there building with LLMs and wondering, hey, how on earth do I actually structure these systems to scale? Well, you're in the exact right place. Let's get right into it. Let's kick things off with a pretty bold vision from Andrej Karpathy. He calls recursive model improvement the final boss battle. I love that phrasing, right? It perfectly sets the stage for what we're digging into today. We are officially stepping out of the realm of sci-fi and looking at exactly how autonomous AI organizations are becoming a practical, everyday reality, step by step. But to truly grasp this massive leap, we need to wrap our heads around this concept of software 3.0. You know, back in Software 1.0, developers painstakingly wrote out explicit, hard-coded instructions. Then, Software 2.0 came along, and we started shaping behavior through big data and model training. But Software 3.0, this is where context and natural language prompts literally become our programmable interface. We are configuring entire autonomous systems using just natural language, completely leaving basic, hard-coded logic in the dust. So, here's our roadmap for the explainer today. First, the micro, Karpathy's auto research loop. Second, the meso, Agent Hub and the DAG. Third, the macro, Anthropic's dynamic workflows. Fourth, the universe, graphs as shared memory. And finally, number 5, the practical build path. Section 1. Micro Karpathy's auto research loop. Let's start small and look at the microscopic unit of this entirely new architecture. This brings us to what Karpathy calls the ratchet loop. Basically, it's a tight, bounded cycle with really frequent feedback. You take a single agent and drop it inside an executable research harness. From there, the agent inspects the code, proposes one specific change, applies it, runs a quick 5-minute evaluation, and then makes a hard, reversible decision. Do we keep it or do we revert? It's a simple setup, sure, but absolutely incredibly powerful. And honestly, the sheer scale you can achieve with just this one simple loop is staggering. We're talking about a single agent running through roughly 700 experiments in barely 2 days. It worked on a core codebase of about 630 lines, and out of those 700 attempts, it actually kept 20 highly useful, solid optimizations. This just goes to show that this pattern isn't just a fluke. It's legible and it's highly reproducible. So what this reveals is our first major architectural shift. The loop externalizes iteration and evaluation. Think about how human researchers operate. We have to hold all our hypotheses and failed attempts right there in our working memory. But this AI loop, it completely replaces human working memory with a durable, machine-readable history. It literally never forgets what it just tried. Moving on to Section 2, Agent Hub and the DAG. Because let's face it, one agent just isn't enough. We need to scale up. Now, when we scale up, notice how agent collaboration totally flips our normal human assumptions about version control completely upside down. Human Git assumes linear convergence, right? Like eventually everything has to get merged into a single main branch. But Agent Git, it completely embraces radical divergence. You can have thousands of agents exploring simultaneously. The main goal here isn't merge this, it's traverse the search graph to explore this massive, sprawling web of both failed and successful ideas at the exact same time. To actually manage all that chaos, Karpathy's Agent Hub uses a super minimal command line interface that basically acts as a graph interface. Agents can fire off commands like leaves to hunt down unexplored frontiers, or lineage to reconstruct the exact ancestry path that led to a specific result. It's massively asynchronously collaborative. It's almost like SETI at home, but for AI agents. Which brings us to our second big principle. A directed acyclic graph, or DAG, externalizes experiment lineage. Because every single commit is a node, and the parent links act as edges, agents can clearly see exactly what work descends from which experiment. This is crucial because it stops agents from just spinning their wheels and repeating the exact same mistakes over and over. All right, Section 3. Macro, Anthropic's dynamic workflows. Zooming out even further now, we land right in the middle of Anthropic's orchestration infrastructure. And when you hit this macro level, the numbers just become mind-blowing. Claude can now dynamically spin up to 1,000 fresh context subagents entirely in parallel. No joke. Instead of some developer sitting there writing a static, hard-coded fan-out script, Claude actually writes a generated JavaScript orchestration program on the fly for whatever the task is. It allocates specialized subagents to chew through massive, complex workloads all at the same time. So, what does this actually mean for us? It means a swarm externalizes parallel search and role specialization. By spawning all these independent, fresh context agents, you are drastically cutting down your real-world wall clock time, all while easily tackling really complex tasks that need to be broken down into specialized pieces. Next up, Section 4. The universe. Graphs as shared memory. Let's push out to the absolute shared universe level and see how all this builds into the ultimate solution for scaling. Now, to solve what we call the context dumping problem, Anthropic relies on a knowledge graph schema to act as this shared, highly persistent memory layer. Think about it. When you have thousands of agents buzzing around, they can't possibly read through every other agent's giant rambling transcript. There's just no way. Instead, the central agent node connects to typed entities, attributes, and tools. Individual worker agents write their structured findings directly to this graph, and then an orchestrator smoothly traverses it to pull all those facts together. This breakdown acts as a perfect cheat sheet for builders. It maps the exact architectural level you need directly to your specific scaling bottlenecks. If you've just got a simple question, hey, stick to zero-shot prompt for the lowest latency. Need to handle repeated feedback? Use a loop. Trying to preserve alternate experiment branches? Go with a commit DAG. But if you have facts that absolutely must survive across sessions, you absolutely need the persistent shared memory of a knowledge graph. Finally, for massive parallel work, a dynamic workflow automates that fan-out. It's all about choosing the exact right architecture for the problem in front of you. Ultimately, our final externalization principle is this. Knowledge graphs store the actual world state. They externalize shared facts, cross-session memory, and crucially, provenance, tracking exactly where a specific claim came from. This is a game changer because it guarantees that when an individual worker agent inevitably drops context and forgets, the overall graph system simply does not. And finally, Section 5, the practical build path. Okay, look, all this high-level cinematic theory is fantastic, but how are we actually supposed to start writing the code for this on Monday morning? Well, this timeline totally grounds the theory in reality. It gives you a staged, step-by-step build path. You do not start with a giant swarm. You just don't. You start on day 1 with a single, measured, reflective loop to check quality. Day 2, you add a tool to reduce known errors. By week 1, you're handling variable tasks with planning. Week 2 introduces multi-agent role specialization. Month 1 gets you a persistent graph for cross-session queries. And by month 2, you are finally hitting that massive swarm workflow for parallel fan-out. You are deliberately, carefully scaling up from implicit, volatile memory into explicit, highly durable systems. But before you go and excitedly hit deploy on 1,000 subagents, you absolutely must run through this production checklist. Remember, autonomy without verification is a total disaster waiting to happen. So ask yourself, is the objective actually testable? Can you distinguish a real improvement with a metric? Can you revert about experiment? Does every single claim have clear provenance? And are your token and cost budgets explicitly capped? You have got to make sure you are retaining human ownership over the specs and the quality bars. I really love this summary quote from the source material. It says, the path from loops to graphs is a path from implicit state to explicit state, and from estimation to evidence. That perfectly captures our entire journey today. We're officially moving away from opaque, messy chat transcripts. Instead, we're shifting toward queryable, composable engineering mechanisms. We're evolving from mere estimation to rock-solid, graph-grounded evidence. So I'm going to leave you with this final thought to ponder as you head back to your own AI projects and start building out your architectures. If your agent forgets, does your graph remember? And as you scale these massive systems, are you just building up fragile, implicit state, or are you actually constructing explicit, durable evidence? Thank you so much for joining me for this explainer, and hey, happy building.